This is the pre-lab talk for experiment number 12, qualitative analysis. This is for Chem 110 lab. In part 1 of this experiment, we will use a series of double displacement reactions and deductive reasoning to identify 6 solutions that could be sulfuric acid, magnesium chloride, sodium carbonate, sodium hydroxide, strontium chloride, and ammonium sulfate. Then, in part 2 of this experiment, we'll use the reactions that we observed in part 1 to construct a qualitative analysis procedure to identify the presence of 4 cations, ammonium, sodium, magnesium, and strontium, in a solution that contains 2 or 3 of these ions. In this experiment, it is crucial to use the paradigm that your observations can lead to conclusions that could be drawn, explanations, and in some cases, questions that are either posed or answered. For today's safety pause, we notice that we are working with 2 corrosive chemicals, sulfuric acid and sodium hydroxide. We'll also notice, we also notice that we are asked to note the odor of our reaction mixtures. It is very important that we do not directly smell any vapors coming from a container. Instead, we use wafting to help fan some of the odor towards your nose in a more dilute way. In this experiment, we will stir the solution with a wooden applicator stick and waft the smell from the wooden applicator stick towards our nose to note the odor. It's also important to note that we will neutralize all acids and bases before disposing of them down the drain. This experiment acts as a capstone of sorts, allowing you to use all of the skills that you obtained in this lab on using your observations to draw conclusions or provide explanations for different phenomena. In the first part of the experiment, you're going to be carrying out double displacement reactions in order to deduce the identity of 6 unknown solutions. There are 3 types of double displacement reactions you will see, and you've probably seen both in lecture and in this lab course. First are the precipitation reactions, which result from the mixture of 2 strong electrolyte solutions to form one ionic compound that's insoluble in water. We can deduce the identity of the insoluble compound using the solubility rules, which can be found in your textbook. Another type of double displacement reaction you'll see in this experiment is the acid-base neutralization reaction, the reaction between an acid and a base to form water and an ionic compound called a salt. Finally, we'll also look at gas evolution reactions, which are actually double displacement reactions followed by a decomposition. The 2 types of gas evolution reactions we'll see are the reactions between an acid and a carbonate compound, and the reaction between a base and an ammonium compound. When reacting an acid with a carbonate compound, you end up forming another ionic compound, carbon dioxide gas, and water. The example shown is a reaction between sodium carbonate and hydrochloric acid, which forms sodium chloride, carbon dioxide gas, and water. When reacting a base with an ammonium compound, a compound containing the NH4+ ion, you'll form an ionic compound, water, and ammonia gas. The example shown is the reaction between ammonium chloride and sodium hydroxide to form sodium chloride, NH3 gas, and water. Another important thing to look at is evidence of a chemical reaction. How do we know a reaction has occurred versus if not occurred? Of course, we know that if no change appears between the mixing of two solutions, a reaction does not occur. Well, what types of things will we look for to see if a reaction did occur? For this experiment, there are 4 things we wanted to take a look at. The first is the formation of a precipitate, a solid compound that forms when mixing 2 clear solutions. We also will look for bubbling. In this experiment, bubbling is evidence that carbon dioxide gas has evolved from the solution. Carbon dioxide is not as soluble in water as many other things, and therefore bubbles quickly out of solution upon formation of an excess amount. Another way to note a gas is by its smell. In this experiment, we're going to use smell to detect the evolution of ammonia gas. Ammonia is much more soluble in water than carbon dioxide is, and therefore will not bubble out of solution quickly. However, you will be able to detect the presence of ammonia gas by its smell, which we'll, of course, safely note by wafting. The final piece of evidence for a chemical reaction is the presence of heat, looking for our reaction mixture to heat up. This is evidence that an exothermic reaction has occurred. And of course, acid-base neutralization reactions, as we learned in experiment 5, tend to be pretty exothermic. Let's take a look at some procedural points for this experiment. It's important to note that typically when we run this experiment, there are two sets of unknown solutions labeled with blue and green. It is also important to note that on my YouTube channel, where most of the lab experiments are, there is a version of this lab that uses the green solutions. For this term, however, we're going to use the blue solutions. I've told the difference by labeling this version B. If you're unsure, it is always a safe assumption to follow the link that's on Canvas, which will take you to the right version of the experiment. You also see that labeling is a very important part of this experiment. Since we're working with many different clear solutions, we want to make sure that we properly label our stock beakers and in some cases test tubes to make sure that we are able to very clearly identify things and that nothing is mixed up. Another important aspect is cleanliness. Contamination can lead to observing an incorrect reaction, which will allow you to make incorrect identifications when you draw your conclusions about either the components of an unknown mixture or the identity of your unknown solutions in part 1. Another important point to make is that some reactions take time to occur. It may take a few minutes for bubbling to be observed or for a precipitate to form, or even for the evolution of heat. Stirring does help reactions to occur faster, as we will stir many of the test tubes for this experiment. But it's also important that some observations may take time to occur. Now let's move on to some very special procedural points. For part 2, we're asked to identify a few different ions. It is really important to note that the sodium ion in this experiment can really only be identified using a flame test. To perform a flame test, we will dip our glass stir rod into the unknown solution and insert it into a Bunsen burner flame, noting the color of the flame. As you might remember from experiment 1, putting compounds that contain the sodium ion in a Bunsen burner flame produces a yellowish-orange color. What you might not remember or have seen is that to identify the presence of strontium ions, A flame test will give a brick red color. Therefore, it is possible to identify strontium through a flame test. However, caution must be taken because if strontium and sodium are both in your unknown, you will only see the flame test for sodium since it gives a very strong result. Therefore, you must do other tests to prove the existence of strontium. Another important point to make out is that strontium hydroxide, if you read your solubility rules, appears to be pretty soluble in water. In actuality, at certain concentrations, strontium hydroxide has a very intermediate solubility in water, meaning under certain conditions you might see the presence of strontium hydroxide, and in other conditions you may not. Therefore, it's very important to note that perhaps in part one, there might be cases where we see a very slight precipitate, which may give away the presence of strontium hydroxide. However, for your unknown solutions, the concentrations will be such that any formation of precipitate, you should actually assume that strontium hydroxide is not the identity of that precipitate, for part 2 only. Another one of these is that the reaction between strontium or between ammonium sulfate and sodium carbonate. You would think that these two compounds do not react, but in actuality they do, to form sodium sulfate, ammonia, and the bicarbonate ion. The ammonia gas, but the ammonia gas that's formed does not give us a strong an odor as adding ammonium sulfate to adding ammonium sulfate to sodium carbonate does not give a stronger result as adding it to sodium hydroxide. And this is because ammonium sulfate is a much weaker sodium carbonate is a much weaker base than sodium hydroxide. So therefore, we may or may not note an odor from a combination of these two. Just a few notes to help you to identify your unknowns in part 1. Okay, hope you enjoyed doing this lab. It's like doing a puzzle. And if you like puzzles, you'll like this lab.